Okay, guys, if I sound a little frustrated on this one, it's because I've already done this and I didn't have my microphone on, so I'm sorry. You might notice that this looks different than our normal PowerPoints. So I'm using the online stuff because I'm going to adopt this book in the fall, so why not? And also because everything's online, so that just helps with everything right now. So at first, this chapter's a little bit wordy. I have to say a lot of things, but you need to stay tuned because it gets kind of intense. So I'm not trying to scare you, I'm just trying to say continue to watch the videos. Alright, so first, this chapter talks about electric charge. You guys have all experienced it. If you've been in a trampoline before and rolled around, your hair sticks up. It's because all of these, your hairs have the same charge in them, and so they're all repelling. If you've ever rubbed your feet on the carpet, grabbed a door handle, shocked yourself, So people obviously realized this a long time before they knew anything about electrons. But it did cause them to wonder what was going on. And so that is where we came up with the word electron. It comes from a Greek word for amber. Okay, so conservation of electric charge, sort of like conservation of energy. It's not created or destroyed, it's just transferred from one place to another in a closed system. There's a net charge. Alright, so electric charge, they did experiments that determined that there were in fact, positives and negatives, which if you've been in chemistry or you're in chemistry right now, you guys know this. You've talked about protons, electrons. So, anyway, the net charge of a system is the algebraic sum. So we do have to do algebra still. And that's going to include both positive and negatives. And an object that is electrically neutral. Obviously, it's going to have the same number of protons as it has electrons. So there will be a net charge of 0. That's like when you say that an atom is electrically neutral, meaning that it's not an ion. So the magnitude of a charge on a proton and electron has the same amount of charge. And charge is given the symbol Q, but can also be given this E symbol, which is sort of like the symbol for electron, or elementary charge, and it has that value, 1.6 times 10 to the negative 19 coulombs. You'll probably use this so much that you'll start to remember it, but, just in case, you probably should write that down somewhere. I would hope that you guys could be able to print this and write this stuff down. If not, I know some of you guys don't have printers. I don't even have a printer. Try to write it on something. Alright, there is some information that you guys will need for homework purposes and quizzes and tests and stuff. Just the masses of protons, electrons, neutrons. I do want to point out that these two right here are close to the same amount of mass. And you can see that the charge for both protons and electrons is 1.6 times 10 to the negative 19th. Just one is positive, one's negative. If you think about it, like if you're looking at the periodic table, let's say like beryllium. Let's see, beryllium is what? Actually, I don't know why I did beryllium and put number 2, so let's do helium. Helium's around 4-ish on the mass number. So for every 2 protons, because that's how you would look at the atomic number, and that tells you how many protons there are in an atom. And then this mass number here, see the atomic number, and this is the mass number. That mass number there, if you take that number minus the atomic number, then you get roughly the amount of neutrons. Now, usually those are in decimals, and that depends on how many types of isotopes there are and percentages, all that stuff that you guys love to do on chemistry calculations. But what I'm trying to get the point of is that there are approximately the same amount. Now, does that always happen? No, but it's approximately so. All right, example 16.1, just so you know, I kicked out part B. I did it and it's fine. It's kind of weird the way that it's asking the percentage of excess electrons, so I just threw it out because I just didn't like it. When you change books, you've got to really go through and everything's different. All right, so this one says the magnitude of charge transferred when you walk across a carpet. You shake hands, unintentionally shock a friend. And it says that it's about 1 nanocoulombs of charge. So this is what I was saying, I think a few weeks before spring break, is that, this is where you really need to start to know what those numbers are on the metric scale, where nanocoulombs would be like 1 times 10 to the negative 9th coulombs. So much easier than going through and doing dimensional analysis. Know that nano is negative 9. All right, so we're supposed to find how many electrons. So whenever you are going to find electrons, you take whatever the charge was, which in this case was 1 times 10 to the negative 9 coulombs, divided by the actual charge of an electron. And, sorry, I didn't write enough there. There we go. Okay, this is 1.6 times 10 to the negative 19th coulombs. So whenever you do that, your coulombs are going to cancel. You're just going to be left with a number, which is fine because you're just trying to find how many, electrons you have access. So you have 6 times 10 to the 9th. So quite a few. That's it for part A. All right, so on the next one, you've got, this is just talking about polarization. So you've got attraction, repulsion, polarization. Okay, so you know that if you have light charges, think about magnets. If you've got 2 magnets and you put the same charges, close to each other, they just push. You cannot get them to go together at all. When you get the 2 unlike charges together, they attract. It's like almost, if you have a good enough magnet, you almost can't keep them apart. So what happens is you have this thing called polarization, which is basically where you have an electrically neutral object, but you can cause those charges to move around if you've got something charged that you can put up close to it. So I'll show you a picture here in a minute. So whenever you do separate the charges, then that's called being polarized. And a polarized object can experience an electric force even though it still has a net charge of 0. So I'll show you here for example, and this is where it's sad that we don't get to do this lab, because this one's one of the funnest labs, I think. Most people tend to like it. What we would do is we would just rub different types of rods. I had rubber rods and glass rods, and I have all kinds of different materials like silk and fur and stuff like that. You rub those rods and they become electrically charged, and then you can hold them up to different things. This one's showing paper, so if you guys have paper that you could just tear little pieces, you just want them little tiny pieces. And then if you had something that was glass that you could rub at home, I would strongly suggest doing it just because it's fun. I do it for my kids, just like we do little science experiments, and they think that's fun. My son loves static electricity. Anyway, you can see that you hold these rods up to this paper, and are they touching? No. They're just very close, and look at the paper. These charges moved over to this side, and these charges moved over to that side. They're still electrically neutral, but now they're considered to be polarized. So this is considered to be polarized by induction. Induction is just a charged object that's moving close to another object and causing those charges to be moved. I put this one on here just because I thought maybe you guys had talked about, polar covalent, things like that. Water is just a really good example because what happens is oxygen has a lot of negatives. So it's like almost partially negative and it's just pulling all those electrons to it. And then hydrogen's almost then over here like having hardly any electrons. So it's like partially positive. That's not an 8. That's like a partial symbol. I don't know. It's kind of a weird looking symbol. But anyway. And if you remember from chemistry, if you have positive and negative, then it's almost like an ionic. But this isn't ionic because it's 2 nonmetals. So, well, really 3 nonmetals. So what happens is these are almost positively charged and this is almost negatively charged. And it creates this weird looking bended bonding that's happening. So, I know you guys go through that a lot more in depth in chemistry. All right. So electric conductors and insulators. So it just depends on what type of material it is, whether or not it's a conductor or an insulator. Materials in which some charge can move easily, that's called conductors. So typically, metals, that can cause the electrons to flow through really easily in metals. They can leave their parent atom and just kind of flow through the whole thing. That's why you see metal in electric wires. Whereas materials in which charge does not move easily, those are insulators. An example of an insulator is like air, glass, things like that. And then the intermediate between conductors and insulators are known as semiconductors. Sometimes metalloids, those are just a few special elements that you've seen on the periodic table that just sort of in that line between the metals and the non-metals. Okay, so charging insulators by rubbing. So you've got some sort of material that you rub the rod with, and you can actually transfer charges by doing so. And then charging a conductor by contact. So before we were showing that it was not actually touching the paper. And what happens when you have the little pieces of paper and you don't touch the glass to it, they kind of float up to it, which is kind of cool. This one, you're actually taking the rod and you're touching the metal and you're separating the charges. And what happens when you touch it, those negative charges then move to the glass rod, so they're transferred, which leaves the sphere basically positively charged. And once that happens, they don't want to be close to each other at all because they're all positive, so they're trying to get as far away from each other as possible. So basically it's just all evenly distributed across the whole surface. Okay, you've probably heard about grounding, a ground wire or something like that. So it's called a ground because basically the earth is what it has to be attached to or in a fashion. So if you were to take this massive amount of, just like one charge or something, you can, say for instance, I just always think of an electric fence at a farm or something. If you touch an electric fence at a farm, you're going to get shocked. But if you take an electric fence and you put it on the ground and it's still active, but you've put it on the ground and you step on it, you will not get electrocuted, because all of those active electrons that would cause you to be charged or electrocuted, they are actually flowing into the ground, and the ground is so massive that they're just flowing through the ground, trying to get away from each other there too. So a conductor is not necessarily discharged when it's grounded if there are other charges that are nearby. So it can actually get charges from the ground nearby too. So this is showing you kind of just a situation similar. So you've got this glass rod that you've rubbed and you've caused, these charges to move to one end. So it's positively charged. You hold it up to the sphere, causing those negatives to kind of move too. Now you can see it's not touching here. So they're not going into the glass rod. And whenever you ground, you see there's this wire that's going to the ground here. Those electrons are now flowing from the ground through the wire to the sphere. And it's becoming pretty negative. When you disconnect that ground, then it's sort of like the opposite of the first picture, where we had all the positives because we were taking the negatives and they were going into the glass rod. Well, now the positives are gone because they have gone into the ground, or the electrons now have come from the ground. Okay? And so now they're just at equilibrium again whenever you move the glass rod away. Okay, so example 16.2, I'm going to stop the video and start a new one before we do this one.